Okay, thank you very much. So I want to present to you one part of my work on towards optoelectronic device and fluorination increase open circuit voltage based on Dithieno-Pyrrol-Quinoxaline copolymers for organic nanotechnology device. I'm Dr. Simplice Koudjina, assistant professor in National University of Science, Technology, Engineering, and Mathematics of Benin. I'm audible?
Yes, you are audible. We can hear you.
Okay, thank you. So
all right.
My presentation can follow this outline, and then I present to you the Africa and the South Africa, where the Benin is, and my country also, director of my university, University, and our 62 Day of Independence. Then, so you know that in this last day, human activity are increasing, and they need also the energy. So energy need demand energy on the fossil combustible, which are decreasing every year, and create another problem of the environment as greenhouse gas effect and the nuclear disaster. At the level, we need renewable energy or green energy, and then from this energy, we can have the wind energy, biomass energy, geothermal, and hydraulic also. So solar energy, which comes with 10,000 terawatts, 40 minutes, the sun comes from on our Earth. This energy is renewable energy and non-pollutant energy. Then you'll be able to develop a lot of material to collect or to record this energy. As you can use the solar inorganic, that is the photovoltaic plaque. This photovoltaic plaque are more cost, more heavy, and more flexible and not flexible. You can use UV visible absorption through blue anti-reflection. And then these materials are being making with silicium. And then we have solar organic, which is less cost, less heavy, more flexible. Absorption UV visible through homolumo level. So when you make this material, you take care of from the morphology surface as the photoactive layer appreciation and the photophysics behavior of the semiconductor, which are related to the efficiency for applicability in another device as OLED, organic light emitting diode, organic transistor, or organic photovoltaic. So these two kinds of structure have not the same thing of functionment. We have for organic photovoltaic emission, and we have cut directly the solar energy and give electricity, but OLED can cut the energy of sun and give directly the light. So to build these two kinds of dispositive or device, we can use the device as the sandwich between two kinds of material, ITO and aluminum. And in it, you have the different device, different polymer combined in it. Then for OLED, you have one transparent anode and whole transport layer for emission, for emissive layer, and electron transport layer, and the cathode. That is why the OLED disposable can be built in. And OPV, one, organic photovoltaic, we have transparent anode, whole and it, we can have a whole transport layer, electron transport layer, and cathode. we can have another part, the discotic construction of these materials. And then we can take care of structure, property, relationship, and probability calculation. This dispositive, organic photovoltaic device, and this structure. From the anode to cathode, we have whole ejection layer, whole transport layer, emission layer, electron transport layer, and interlayer also. And then we put now metal oxide and cathode. We make substrate to protect the surface of the cathode. This device building can be also tried by vapor deposition in the laboratory. So why this material can capture the solar energy and give electricity. So when the sun comes from on the surface of the material, we have the dissociation of the exciton, the electron, and the hole. The electron can go to the cathode and the hole to the anode. The displacement can be measured from photovoltaic open circuit device and the current density. And then we can measure the maximum power by this mathematical formula and the power conversion efficiency and the photovoltaic values. And then we can measure this device by preparing the organic structure. We bigger by voltaic drop and by reduction in the drawing force to have a very or to check the quality of the photovoltaic device. And then from the quantum chemical calculation we are doing, we begin from the ground state and we make the calculation, and then we can make the calculation on the excited state and have another parameters as mobility, as an interface DAP, and the combination energy can be care to extract then the energy on the surface. So general goal of this work is to explore by method of quantum chemistry the way to design, predict, interpret, and improve the intrinsic optoelectronic property of some physical chemical materials. At the level, we propose some technique to enhance the VOC or the morphology or the charge transfer of this OPV. Band gap homolumo can be extracted, morphology also of the photoactive layer for type, voltage enhancement, and charge transfer. This work are being in the method in three laboratory of electrical chemistry, laboratory of electrical chemistry in Belgium and in Benin. So the material monomer has been building without fluorine for the first time, that is the monomers, and second time with one fluorine for this monomers and two fluorine for this monomer. We are building the dimers for this type of structure. And then we are using the mathematical formula for Marcus and Concha.
You have 1 minute left.
Okay, to make our structure. And then we are using another kind of a functional, exact correction functional to make our calculation. Then we can make this chart separation. Another structure can be made from donor and acceptor parts. And then we can see the synthesis in organic side and theoretical side. And then on this result, theoretical homolumo can be calculated and the experimental also. And then the result can be this slide. And then the AFM structure can be built also to check the morphology activity of this kind of molecule. In conclusion, we have successful synthesis and fluorination can be used to turn on the optical electric property for this device. Outlook is there, and then we thank everyone for this kind attention. Thank you.
Thank you very much. Thank you very much for your presentation.